So I entitled my talk Three-Dimensional Waterways, but really it's a bit more specialized than that. The title should be Three-Dimensional Solitary Gravity Capillary Water Waves. So let me start before I do anything by just outlining the version of the problem I'm interested in, and then that's what we're going to talk about. And then I'll just say a few remarks about other 3D waves at the end of this. So here's the setup again. You've seen this quite a few times today. So this is a three-dimensional fluid this time. Yeah? So I got the usual coordinates. Y is always pointing upwards in my notation. X and Z are the horizontal ones. It's going to be a perfect fluid. So homogeneous, inviscid, incompressible. And I'm going to be talking today only about irrotational flow. So the velocity field will be the gradient of a velocity potential, which will be harmonic in the fluid domain. There it is. I've got a bottom at y is equal to 0. And there I don't want any water to get through. That's, the impermeability condition. So there I've got the Neumann boundary condition. And then we've got the usual two nonlinear boundary conditions at the free surface. Here they are. This is the kinematic boundary condition. That's the condition which says no water gets through the free surface. And the dynamical boundary condition, this is the condition that says that the pressure is proportional to the curvature at the free surface, so it's balance of force basically. And here that's the acceleration due to gravity, and that is the coefficient of surface tension. And in everything I'll talk about today, this sigma will be positive. Okay, I always put these remarks are kind of pointless for this audience, more or less. You know this, but it's worth saying it every time. Why is it hard? Firstly, it's a free boundary value problem. You don't know the function eta to start with. You have to find it as part of the problem. And then you've got these two very unpleasant nonlinear boundary conditions at the free surface. Okay, so I'm interested then in solitary waves. So those are waves which move in a fixed horizontal direction with constant speed. Now there's no loss in generality in assuming it's the x direction here. The equations are all invariant under rotations in the xz plane as I've written them. So let's say it's the x direction. So eta and phi will depend just on x minus ct. And the solitary wave condition is simply that the wave goes to 0 at large distances, forwards and backwards in the direction in which it's traveling. What it does in the other direction, Z, is open for debate, and we'll talk about that in a moment. Before I forget, I'm now going to change to the moving frame. So x will always be an abbreviation for x minus ct in everything that comes now. And here you can see that I haven't adjusted yet to being back in the UK, because this should be parameters and not the German word parameter. I had a bit of a shock yesterday, Stephen, and I realized that some of the words on some further talks were written in German. I didn't even notice. When you non-dimensionalize this, you find that there are two parameters in the problem. Here they're called alpha and beta. For those of you who heard talks by me before, these are not the same alpha and beta that I usually use in talks. This alpha is the square of the Froude number, so if you like, it's the dimensionless speed. And this is the Bond number, it's not the Weber number, that's what I usually call beta, and it measures the strength of surface tension. So if you like, alpha is the non-dimensionalized speed and beta is the non-dimensionalized coefficient of surface tension. Okay, so that's the problem I'm going to talk about today. And what we're going to do is to construct solid wave solutions to this problem. Now I'd just like to make a few remarks at the beginning. This is joint work with a number of people, and it's work which has been going on a long time. Some of the results, I'll tell you, are quite old, and some are very new. So the collaborators I've been working on this with are Mariana Haragus from Besançon, Shuming Sun from Virginia Tech, and Eric Wahlen from Lund. We're going to talk about different values of surface tension, strong and weak surface tension. Some are more physically relevant than others, and various people have been collaborating in various aspects of this, but I'll just put them all together in this collection. What I'm talking about, actually, maybe I grouped the talks today in an unfortunate order, because the last two talks definitely had a connection with singularities, and my talk has a strong connection with the talk of Guido Schneider this morning, in that what we're going to do really is to justify model equations. Now, we had a bit of a discussion about this after Guido's talk as well. The idea is you derive a model equation by some asymptotic procedure, and then this predicts solutions, and maybe those solutions agree well with numerics or experiments. You think it's a good model, but nevertheless, it's mathematically a reasonable thing to do to ask, well, okay, what is the actual mathematical justification for what we're doing? Guido's approach was then to say, okay, well, let's show that in the right parameter regime, the model equation itself captures the dynamics it's supposed to capture over the right time scale. My approach is a bit different. It's simply this. There'll be model equations which predict the existence of certain types of solitary waves, and then we'll show that those waves exist as solutions of these equations. Yeah, so it's a little bit different in approach. Okay, now as I said, that's the version of the water problem I'm going to talk about. There are other results on three-dimensional water waves which aren't covered here. Without surface tension, there are the traveling wave solutions constructed by Bios and Plotnikov. Those are doubly periodic waves. Doubly periodic means periodic in two horizontal directions, traveling in possibly a third direction. That's a technically very difficult problem which involves small divisors. I'm not going to talk about that today. And in the context of traveling or steady gravity capillary waves, there are also a large number of exotic solutions which were constructed by me with several other collaborators using spatial dynamics methods. I'm not going to talk about those either. And then there are doubly periodic waves with surface tension, which were constructed by Walter Craig and David Nichols, who's here at the front, and have been elaborated upon numerically and mathematically by basically David in collaboration with several other people. So I'm not going to talk about those results today either. I'm just going to focus on this particular problem. Okay, so I think that's all the preliminaries to this. Let's have a quick look then at the type of waves I'm talking about. There are basically three types of solitary waves of the type that I mentioned before. Let me just go back a little bit to this, sorry. Should have said this already. So you see here, I've got waves moving in the x direction. They're supposed to decay to zero far up and downstream. I don't need to say that they should be non-trivial, right? I mean, eta is equal to zero is a solitary wave according to my definition. It's not a very interesting one. You know? But depending on what it does in the z coordinate, the transverse direction, we can classify them in different ways. So let's come to the first group. So the first type of wave is kind of a trivial one in 3D. It's the line solitary wave. Yeah? So here you can see two examples of it. These are artists' impressions of the free surface, but they're relatively realistic. I'll say a bit more about that in a second. You see here the free surface only depends on the direction which it's traveling. It's constant in the other directions. So I call those line solitary waves. The free surface is just a line, just a curve. Yeah? Now, I've distinguished two values of beta. I've called them strong surface tension, weak surface tension. Beta is the Bond number, so the non-dimensional surface tension. And for reasons which I will explain in a moment, I believe that for strong surface tension, the free surface looks like this. It is a wave of depression. It's always negative. And for weak surface tension, I have a modulated envelope which looks like that. Yeah? The second thing a solitary wave could do is it could have the pulse profile in the direction of propagation. Has to have that, but it could be periodic in the transverse direction. Yeah, so here you see a wave which has that profile in the transverse direction, but it's periodic. Sorry, I said that wrong. It has this profile in the direction of propagation, but it then has a periodic perturbation added onto it in the transverse direction. I've done the same thing on both of those. Yes? Now, this sketch is that the scales are exaggerated here because the proofs which I'm going to give to you show that there are waves of this form, but the periodic modulation has a very long wavelength. Yeah, and obviously, I mean, I don't have enough screen to draw that on, so here it doesn't look like it's a very long period, but it should be a very long period in the transverse direction. Okay, and here I've coined the word dimension breaking. This goes back to Kirschgessner. And this is where the work all started with Kirschgessner and Haragos. They looked at dimension breaking phenomena for various types of equations. And dimension breaking simply means if you start with something which only depends on one of the physical coordinates in the problem, here the direction in which the wave is propagating, they could bifurcate in a secondary bifurcation from those waves which depend on more than one physical direction. In this case, you can see you've got a line wave. A periodic modulated wave is coming from it in a dimension-breaking bifurcation or phenomenon. Okay, so again here you can see the periodic modulation superimposed on it. The wavelength should be long. Okay, and then we come to the third type of wave. I did these plots. I didn't have time to get the color the same as on the previous transparency. I usually put a lot of trouble into making the diagrams consistent, but I didn't manage it this time, I'm sorry. This time, the waves are fully localized. That means they decay to 0 in every direction. But remember, they're still solitary waves. They move in the direction shown by the arrow with constant speed. Okay? Now, there are various ways of thinking about this. You could think, well, maybe those are the periodically modulated waves in the limit as the period goes to infinity. And that's sort of what you see here, right? The profile in the direction which is propagating here is the same as in the wave you saw on the last transparency. That's same here as well. You see the oscillations? Yeah? But then in the transverse direction, we now have a monotone pulse-like profile superimposed. Yeah, the scales have been exaggerated here again so you can see the features. This wave looks like it's very deep with a sharp corner. It isn't. It's very small amplitude. I've just exaggerated the scale so we can see it. And I apologize, I didn't have time to play with the pictures to get them looking optimal. But I hope the main features are there for you. Yeah, and so if we just look at these, a few remarks to make about these. These waves are not radially symmetric. Yeah, they're also not monotone. Let me say this properly. They're symmetric with respect to the two axes separately, but they aren't radially symmetric. This wave isn't monotone in this direction, but it is in the other direction, and the same here. You have exponential decay in this direction here, but not in the other direction, and this wave decays to 0 algebraically in all directions. Okay. Now then, before I continue with this, I'm going to carry on with motivation for why I think these waves exist in a moment, but I'd just like to say that we've already seen some of these waves in the conference, and people have been involved in computing them numerically here. There are computations of these based on numerical computations of the Euler equations, on model equations by Milewski, by Wang, by Vandenbroek, and by Kucker and Parau. So these types of waves have been computed for Euler and for other types of model equations many times before. What I'm talking about today then is existence proofs for these, for the Euler equations. Okay, so let's do a bit of modeling first. Now I'm more a pure mathematician and applied, but nevertheless I can do modeling if I'm forced to. And so I'm going to do some. I just want to give you a kind of heuristic argument why I think those waves exist and why they look like they do. Yeah? So let's look at the two cases of strong and weak surface tension separately. Now, the first thing you do when you look at water waves, of course, is you compute the dispersion relation. That's waves traveling with different speeds. Waves with different frequencies will have different speeds. So let's look at periodic traveling waves and plot the dimensionless speed alpha against the frequency, or the wave number, I should say, mu. Yeah? And then you get a plot for a strong surface tension which looks like this, monotone increasing, and the limit here is 1. Yeah? And if you see that and you know a lot about modeling, you say, aha, yes, I know how to derive a universal model equation for that. What I should do is make an ansatz like this in my equation. Eta is the free surface, I scale it like this, so I've got long waves in the x direction, very long waves in the z direction, small amplitude, and then a higher order remainder. I'll take the alpha in my problem, so what's the epsilon here? It's a perturbation of alpha about 1, and I'll make the perturbation just underneath. The idea here is that I'm looking for long waves, so solitary waves, and I don't want any periodic waves to kind of resonate with them, so if I'm slightly under 1, then I don't have any traveling linear periodic waves of the same frequency. And then we've had this said a few times in the conference already, then an undergraduate student can do this now. Then you plug this ansatz into the equations, you expand it all in a sea of powers of epsilon, and at the first, when you start to equate coefficients, the first non-trivial equation that you get out of this is the KP equation, which I've written down here. Yeah? So that's an equation for the zeta which you see here. And so the point here is that equation indeed has line wave solutions, periodically modulated solitary wave solutions, and fully localized solitary wave solutions. They're explicit solutions, in fact. You can write them down and plot them, and they look just like the pictures I showed you on the previous transparency. So if you believe that the KP is a good model equation here, then you should be expecting to find these in the equations. I've just written down the KP in a slightly different form here for reasons which will be clear at the very end. Yeah, so I mean, this is a very trivial thing. All I've done is integrate twice with respect to x. Yeah, now we can write down in function spaces the exact sense in which this equation should hold and the exact sense of that inverse derivative there. But let's just keep it at this level for now. This suffices to understand what's going on here. Okay, so very good. And that's strong surface tension. Okay. Now let's have a look at weak surface tension. This is the physically more interesting case. So weak surface tension is beta less than 1/3, and then when you plot the dispersion relation like before, now you have a different shape. The global minimum is now at a non-zero wave number, let's call it mu0, and you have a critical speed alpha 0 there. Yeah. Now I'm actually going to use alpha 0 and mu0 with respect to the Kp thing which we just saw, but then mu0 will just be 0 and alpha 0 will be 1. Yeah, so I'll combine the two things a bit later, and I'll probably forget to say this again, but I'll say it now so that later I can claim that I did say it. Okay, and if you see that dispersion relation and you're looking for a universal model equation, then you make this ansatz. Yeah, here it is. Zeta this time has got the same long scaling in x and z. The amplitude is also epsilon, and here you've got a carrier wave which is being modulated. And again, you write alpha as a small perturbation of alpha 0. You want it negative so you don't get interference from linear traveling waves, which are periodic. And then you put that into the equations and you expand that in a sea of epsilons. And it's a more unpleasant calculation than the one you did before. And I have actually done it, it really is unpleasant. And that's what you get, the Davis-Stewartson system. You know? I should mention here, some people know about this, some people will recognize the coefficients have been fiddled here. There are coefficients here, I've set them all to 1 just to make it simple for the transparency, right? Okay, so don't get angry or upset about this. And again, the point here is that the Davis-Stewartson system admits line solitary waves. That's easy to see because if you just put Z, just get rid of the Z dependence, then you end up with just the nonlinear Schrödinger equation, which has an explicit solitary wave solution. It also has periodically modulated solutions and fully localized solitary wave solutions. Those you can't find explicitly. You have to prove they exist, but the proofs are available in the literature, and when you take a look at them, then they look like the solutions I've plotted as well. And once again, here's the thing written as one system. All I've done here is I've just solved the second system for psi as a function of zeta and plugged it into the first one just to get one equation out. And again, don't worry about the meaning, the exact meaning of that. That will depend on the function spaces in which you look at this equation later. The point is simply that you can do this at a formal level and you can make it work rigorously as well. Okay, so very good. So now we believe, these are systems which have been studied a lot, and they're universal model equations, and the question is, are the solutions which they've just predicted really solutions of Euler? Okay, so what's new and what's old here? At the beginning I said some results are new and some are old. The old results are the results for strong surface tension, beta bigger than 1/3. Those are results which I, in fact, was starting to work on at the time of the last program here in 2001, and some of the things which were said in that program encouraged me. And in the last few years, well, last 2 years maybe, I've taken this up again, and I've now got the results for beta less than 1/3, which is the physically more realistic regime. And that fits in really well with, for example, last week we had this wonderful afternoon about 3D solitary waves numerically and modeling, and this fits in very, 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 very well with that. I'm very pleased with the fact that there's resonance between the various communities, that we all think the same questions are interesting at the moment, at least for this. Okay. All right then, so what I'm going to do now is just to give you a flavor of the existence proofs. I'm going to keep it at a very simple level. They really aren't that difficult. There are some technical difficulties which I'm not going to show you, and some of the computations are really rather lengthy. I'm just going to give you the main ideas, and I think the main ideas are actually very simple. Okay, let's quickly dispose of the line waves first, because these really are old results, and Guido mentioned these this morning in the conversation after his talk. There are now there have been existence results for the line solitary waves for a long time. They go back to Amick and Kirschgessner in 1809, although Kirschgessner actually had them by essentially the same method 1 year earlier, 1988, in a different paper. And Jus and Kirschgessner in 1992, those are for beta bigger than 1/3, beta less than 1/3, so weak and strong surface tension. this is where the main result appeared, but then there were some technical details which still had to be filled in. That came a year later by Jus and Perroem. And there are versions of the existence result here for infinite depth as well. I'm not going to talk about those. Okay, so let me just say what the results are. The result of Amick and Kirschgessner is, for the regime in which we were talking about, that was alpha is 1 minus epsilon squared, there is indeed a line solid true wave to the water wave equations. It indeed looks like the correct scaling of the KdV wave of depression, there's a plot of it right there. It's what we were looking at a few transparencies ago. The Jus and Kirschgessner result is in the regime we're interested in for weak surface tension, there are at least 2 line solid true waves described by solutions of the NLS equation. Here they are, and here is the corresponding plot of the free surface. Okay, the method is basically you formulate the system as an evolution equation in which the x coordinate, or x minus ct if you like, is the time-like variable, and you show that it has a finite dimensional invariant manifold. It's 2-dimensional in this case and 4-dimensional in this case, and on it there is, well, in that case at least 1 homoclinic solution, in this case at least 2, and those give you the waves you're talking about. That's how it works. And this method has now become sort of semi-classical. It's been used for a wide range of problems, but the water wave was one of the most important applications back, 20 years ago now. Yeah? There are more exotic varieties of these as well. With Buffoni I constructed ones which look like multiple copies of these glued together, but we won't really talk about those too much today. Okay, so let me come then to the 3-dimensional part. That's the periodically modulated solid true waves, and I've already mentioned the method. You formulate your evolution equation as an evolutionary equation in which a spatial direction is the time-like variable. That's become known as spatial dynamics. And that's in fact how you find the periodically modulated solid true waves. Let me show you how that works. You take the water wave equations, which I had before, and you formulate it as an evolutionary equation. So here's an evolutionary equation. L and N, those are just, the linear and the nonlinear parts. U is some combination of the variables you had at the beginning. I'll tell you exactly what U is in a moment. I won't hide that from you. But this is just to get the idea. And you see what the time-like variable is here? This is Z. You see that's the spatial direction which is transverse to the direction in which the waves are traveling. Okay, now let's look at that in a phase space. So this is some function space X of functions which vanish as X goes to plus or minus infinity. So in other words, our phase space, every point in our phase space is basically a solid true wave itself, or a line solid true wave, if you like. Yeah, it's a function which decays to 0 at large distances in X. So you're passing through a phase space, every point at which has the pulse-like profile in X. Now then, let's think about the consequences of that. An equilibrium solution of this equation must therefore be a line solid true wave, because it does not depend upon Z, that's the definition of equilibrium, and it has a pulse-like profile in X, just like everything in the phase space does. So it must look like that. Constant in Z, pulse-like profile in X. It must be a line solid true wave. On the other hand, if you're periodic in time, periodic in Z, then you must be periodic in this direction. But you're passing through a phase space where every point is a wave which is pulse-like in X. So a periodic solution to that must be a periodically modulated solid true wave. And here you can see the sort of situation I'm really interested in. This is an equilibrium in the phase space which is surrounded by periodic orbits. Yeah, it's stylized here. They're not going to be exact circles. But if I can find that, yeah, this equilibrium will give me a line solid true wave, and it will be surrounded by orbits which give me periodically modulated solid true waves. And that situation is exactly the dimension breaking situation. This wave the dimension of this wave will break and turn into this wave. Okay, so that's what we should do then, right? I mean, we know that there are line solid true waves corresponding to KdV or NLS, or beta bigger than 1/3, beta less than 1/3. We saw that in the previous transparency. Those are the results of Amick and Kirschgessner and Jus and Kirschgessner. So we should look for periodic orbits which surround them like this. And then we will find periodic modulations of those waves. Okay, so how to do it? We'll use the Lyapunov center theorem. Yeah, this is what you do. Again, it's a nice thing to do to say, yes, undergraduates can do this. And they can, well, in theory. What's the Lyapunov center theorem? It says, okay, here's a Hamiltonian system written in its canonical coordinates. Here, this is just q is dh by dp, p is minus dh by dq. I suppose it has n degrees of freedom. Now, suppose you have an equilibrium and you linearize around it. And you find that you have a pair of purely imaginary eigenvalues. I've called them here plus or minus I omega. And the Lyapunov center theorem basically tells you that the linearized theory is correct. What would linearized theory tell you here? It would tell you have a center, right? And the Lyapunov center theorem says, well, okay, if it's a Hamiltonian system, then the linear theory is correct. You do have a center. And so you have a family of periodic solutions. You know, their small amplitude and their period tends to, their frequency rather, tends to omega as the amplitude tends to 0. Okay, now there's a catch, there always is, but it's a very small catch. The catch is the non-resonance condition. What you don't want is for any integer multiple of these to be an eigenvalue either. You don't want any resonances. Yeah? And that's it. I mean, that's the Lyapunov center theorem. So that's what we're going to try to do. Yeah? We know that the line solitary waves are equilibrium of our spatial dynamics formulation. We're going to calculate the spectrum around them, and we're hoping to get that picture. And then we're going to say, okay, then we can use the Lyapunov center theorem. We'll get periodic waves, periodic orbits surrounding them, and those will give me the periodically modulated solutions. That's the idea. Well, you know, I mean, things aren't always quite as simple as that. There are some complications here, but there are some extensions of the Lyapunov center theorem as well, which are very helpful. First of all, everything we're doing here is actually in infinite dimensions, right? Not in finite dimensions. But that's actually no problem. There are two extensions here due to Devaney, one of which basically says, well, everything works in infinite dimensions as well. You have a few more technical conditions on the linear operator, but those aren't so hard. And in fact, you don't even need the Hamiltonian structure. It's enough if the system is reversible. What does reversible mean? Reversible means that there's an operator S which anti-commutes with the vector field. Yeah? In other words, if you change the direction of time and you operate on an orbit by S, it'll give you another solution. It's just a way of saying that the system has a time symmetry. Okay? There's another extension which is due to Jos, which is very helpful here. In fact, and I think this was mentioned in one of the talks yesterday as well, when you're working in infinite domains, as you will be if you're going to linearize around solitary waves, essential spectrum tends to come up. That was you, wasn't it, Vera, yesterday in your talk? Essential spectrum tends to come up. So you're not going to be able to avoid it. And in fact, what will happen is when you calculate the spectrum around one of the linear waves, you will find that there's essential spectrum along the whole of the real axis. And this will mess up your non-resonance condition, yes? Because 0 is in the spectrum now, so it's resonating with these two eigenvalues. But Jos made a very helpful and very simple observation. Just look at the proof of the Lyapunov center theorem. You don't need that there's a non-resonance condition at 0. All you need is to be able to solve this equation. You need to be able to invert L on the range of the nonlinearity. When you just look at the proof, that's what you see you need to be able to do. This is something which you can always do if 0 is not in the spectrum. But if it is, you might still be able to do it. Because having essential spectrum is just basically a restriction on the range of L. Yes?
That's a good question. Essential spectrum, is it a continuous spectrum?
Continuous spectrum, yes.
We call it continuous.
We call it continuous spectrum, yeah. Yes, okay.
Yeah.
I always say it's essential spectrum because there could be eigenvalues of infinite multiplicity there as well, and I wouldn't call that continuous spectrum. But in this case, it is continuous spectrum, yes. Okay. All right. So now we're experts on the Lyapunov center theorem. Yeah, and we know what to do. What we need to do now is then to formulate our water wave problem as an evolution equation of this type, linearize around one of the line solitary waves and calculate the spectrum. Okay? And let me just show you how to formulate it as an evolutionary equation. This is a transparency which I've shown in many forms and in many audiences over the last few years. So some of you have seen this before. And this is something which an undergraduate student really can do. It's a really very direct, explicit calculation. What I want to do is to formulate the problem as an evolution equation which z is the time, and the key to it all is a variational principle. It's this variational principle due to Luke, 1967 in the Journal of Fluid Mechanics. Here it is, written down in the non-dimensional coordinates. Those of you who've seen this before, you can see that the alpha and the beta are in slightly different places to usual. That's because of my different definitions of alpha and beta this time. Yeah. Now, this is kind of a useless variational principle in some ways. The main problem with it is you have a variable fluid domain, of course, yeah? So you see the velocity potential actually depends upon the height of the free surface, trivially by the fact that the domain depends upon eta. Now, when I was a very young man doing my PhD, I didn't know anything about sophisticated mathematics, so I decided to use the crudest weapon possible. I said, well, let's get around the problem. Let's just rescale. Let's just put a new vertical coordinate y tilde in by scaling the old one by the height. Yeah, so y tilde would be in 0 to 1. And then introduce a new capital phi just by changing y in the velocity potential. And if you put that into the variational principle and write it down explicitly, you get a new variational principle. Looks like this. And now the coordinates are eta, phi, eta z, and phi z. Yeah, so it's an explicit thing. I just haven't written the formula down here because it's a bit long and it's not really so interesting for us. So David's smiling because this is exactly what he's been doing for some time in doubly periodic waves. This is a very effective trick. It's very simple and very effective. But there are variations of this now due to David Lan and his collaborators in which you can use more sophisticated waves to map this thing to a strip than just scaling by the height. And then that has advantages in initial value theories and so on. But that's not relevant to us today. Look at the structure of that, though, the way I've written it down. It's an integral over z of something which depends on eta and phi, eta z and phi z. Well, think of classical mechanics. Doesn't it look like Hamilton's principle to you? Those are the q's, eta and phi's. Those are the q dots, eta z and phi z. So what do you do in classical mechanics? You introduce the p's, yeah, the derivatives of this thing with respect to the q dots. You invert these equations to get the q dots as functions of the q's and the p's. And then you write down the Hamiltonian. It's the scalar product of the q dots and the p's minus the L. And then Hamilton's equations, they are just q dot is dh by dp, and p dot is minus dh by dq. Did I say that the right way around? I think I did. Okay. And in fact, you can do this explicitly, and at the end, you can write down these equations explicitly as well, and you have formulated your problem as an evolutionary equation in which z is plays the role of time. It's a very simple calculation. These equations can be written down explicitly, but they would take two transparencies if I wrote them down. I mean, they're long formally, but there's nothing of intrinsic interest about them. That's why I've hidden them from you. And I mean, it's the end of a long Spitalfields day, so I know you don't want to see lots of complicated equations. There's reversibility, and it's the classical reversibility. It's just q goes to q and p goes to minus p. Yeah, so you have all the ingredients you need to do what you want to do. What you want to do is to, when we come back here to the this transparency, you want to linearize around one of the line solitary waves, let's call it u star, and you want to show that the spectrum looks like this. And once you've done that, you can simply apply the Lyapunov center theorem and you have your periodically modulated solitary waves. Okay, let me just give you a very quick idea how to do this. This is probably the most technical transparency on the whole talk. Yeah, so this is the spectral problem. You want to invert L minus I lambda u is equal to some right-hand side, because you want to discover whether lambda is in the spectrum or not. I'm already assuming that the action is for long waves, so instead of lambda, I've got epsilon times k, because I'm assuming the things are going to be long, so I know I have short wave number. Okay? With the alpha as before. Okay. So this is all written in compact form, yeah? But this is really a very amazing thing what happens. You remember on the previous transparency there were equations, well let's have a look. There were these four equations, so there are four variables here, four unknowns. Eta is really the height of the free surface, and those are some kind of related to eta and phi somehow. In fact, you can solve for all of those as functions of eta on the right-hand side, explicitly. One of the, I mean, for the omega and the psi, you can just write it down. For the phi, you have to solve a boundary value problem, so you have it in terms of a Green's function, but it's all explicit. Yeah, so now you just have an equation for eta is equal to some right-hand side. Okay, this is a Fourier multiplier operator, yeah, so what this means, g of d acting on eta, you take the Fourier transform, then you multiply by the g, and then you take the inverse Fourier transform. That's my notation for g of d. It means take Fourier transform, multiply by g of mu, take inverse Fourier transform. Okay? All right. And then, oh, sorry, I'm
a little confused. I thought you were linearizing about a solitary.
I am.
And it looks like you're linearizing about the trivial state.
No.
G of mu looks like the one for the trivial state.
Yeah, but there's a difference between wave number 0. I mean, I've got wave number 0, which is where the action is, or the wave number mu 0, and I've got these equations, yeah? What I've done in here, I should maybe say it a bit more carefully. I've taken the line solitary wave, I've linearized the equations by hand around them, and that's the equation you're looking at the top.
Okay, that's the
Yeah? And then I look at the spectrum of that. Yeah? I mean, I'm running into a bit of danger because I didn't want to show long formally, so I've compactified everything, and then of course it, you know, but this L is the linearization around a line solitary wave. You already have it explicitly, well, an asymptotic formula for it explicitly at least, because you have that for the line solitary waves. All right? And you do what I say, eliminate the other variables, and you get to that. Okay. This is just a remark for those interested. In fact, this g of mu, this multiplier, is positive with equality if and only if you're at plus or minus mu 0. What does that mean? The action, and Guido said this, Guido had really much nicer pictures than I did of this particular thing. The action is all around mu is equal to 0 if your beta bigger than 1/3. That's KdV, Kp. Or around the points mu 0 minus mu 0 if beta is less than 1/3. That's nonlinear Schrödinger, Davies-Stewardson. Yeah? Okay. So, and here I've lumped this into one. Mu 0 could be 0. So what we're going to do now is take the eta and split it into two parts. A part which is concentrated around plus or minus mu 0 and the rest. Yeah? And then you get two equations like this. You're simply multiplying by cutoff functions. That's all it is. Yeah? And now another miracle, well, if you look, when you do the mathematics, it's not a miracle. You can actually solve for eta 2 as a function of eta 1. Yeah? And now you've got one equation for eta 1. You plug this for eta 2 back into the first equation. You've got one equation for eta 1. Okay? Now you've localized near the spectrum. And now you just do the scaling, which we had at the very beginning for KdV or Davies-Stewardson on the eta 1. Plug that into this equation and expand in powers. Yeah, and what you find is exactly what you would expect, I guess. If you're doing modeling, this is no surprise at all. What you will find is you have a perturbation of the Kp equation linearized around the line solitary wave, or a perturbation of the Davies-Stewardson equation linearized around the line solitary wave. Okay? So, and that's what this is showing here. That's the Kp equation linearized around the line solitary wave, which is with the star. This is the ds equation linearized around the line solitary wave, which is a star. You've got the plus k squared psi coming from the spectral parameter in the problem we just looked at, and then some right-hand side. And there's the perturbation. It's all something of order epsilon. Okay. And now I can explain the rest. The rest is just written down here. Obviously, B0k, write the equation like this. This B epsilon k is what you see over here, plus the k squared psi is equal to some right-hand side. When I put epsilon is equal to 0, those terms drop out, and I have an operator which I know explicitly. Here it is. It's that or that. It doesn't, in fact, depend upon k. And its spectrum is known explicitly. You can go away and look in some books. Yeah? And in fact, you do some spectral perturbation, and you find that the spectrum of B epsilon of k looks just the same. Here it is. It's got one negative eigenvalue, and it's got continuous spectrum from 0. I say it's continuous spectrum there. I took your comment into account. The whole of the positive axis. Okay. And looking at this equation, you can see then that this form here is B epsilon k plus k squared is equal to the right-hand side. So you're going to be able to invert this equation if the lambda epsilon k plus k squared is not equal to 0, and otherwise you're going to get a simple eigenvalue. Okay, now it turns out this equation has exactly one solution, k psi. That is a bit annoying to prove. because you do this using a perturbation argument, but you know if you do perturbation arguments using implicit function theorem, you have to have information about the derivative. So you have to go through all this again to get information about the derivative. I'm concealing that from you. And so the conclusion of all this is exactly that you get plus or minus I epsilon k. Epsilon are simple eigenvalues of your operator L, the linearization around the line solitary wave, and otherwise we're invertible. That's basically saying that the picture we've got is indeed exactly that, but we haven't talked about k is equal to 0 yet, and in fact you do get that situation, that you get essential continuous spectrum there. But this is handled in the same way. You just check the Yost condition, which I mentioned. You do the whole thing again with k is equal to 0, and you get an equation which is written like this. You know it for epsilon is equal to 0 explicitly. You know that the equation is invertible, and so it must be invertible for small values of epsilon as well. And so you verified the Yost condition, and you have constructed your proof of the existence of periodically modulated solitary waves. Okay, that is a very interesting problem because usually, there was this comment yesterday, wasn't there, that only women do linear theory? Well, then I must be a woman, because the hard part of this is actually the linear theory. The hard part of this is calculating the spectrum. It's actually a long series of calculations. You have to get it exactly right. Yeah? So what I want to say here is that linear theory is not to be sniffed at. You know, I mean, it can be great fun. Okay, let me conclude then with a couple of an idea of how to do it for fully localized waves as well. Yeah. So here, those are the ways we were talking about earlier. There's the strong surface tension, those are the weak surface tension. Yeah, so this is the KP-like wave, this is the Davy-Stewardson-like wave. And it's a variational argument again, and it's a reduction argument again. There's Luke's variational principle, we just saw it, with the same problem as before. But let's get round that problem now in a slightly different way. Yeah, and Dave's smiling again because he's also used this method. And in fact, you can combine the two ways which we were just talking about. This time, instead of flattening the domain, let me introduce the Dirichlet-Neumann operator. We've seen this many times before as well. Dirichlet-Neumann operator defined like this. Psi is supposed to be the trace on the free surface. The Dirichlet-Neumann operator is done by solving Laplace's equation in the fluid with Neumann boundary condition at the bottom, and the trace is equal to psi. And then you take the Neumann, the normal derivative at the surface, and multiply by this scaling factor. By using Green's theorem, then you can reformulate this in this way, where now this integral over the unknown domain has been replaced by this g, which is the Dirichlet-Neumann operator, and this time the price you have paid is that you now have a non-local operator in there. Okay. So, what you're going to do with it? Basically, it's the same thing as for periodically modulated waves, but now it is nonlinear. But it's basically the same procedure, and I mean, this is remarkable. The actual approach goes somehow back to Buffoni. He was the one who first tried to do this. And there's some, well, when you do it a few times, you don't think it's surprising anymore, but the first time you do, I think it is. It's basically the same thing I just told you a few minutes ago, but now in a nonlinear framework. So we write down the Euler-Lagrange equations for the functional, which is shown here, this variations of this functional. That functional is now called f. Yeah? And you have two equations because there were two variables before, eta and phi. And now you solve for phi as a function of eta. What I thought was amazing is you can do that explicitly as well. Look, here it is. Yeah? And then you define a reduced functional by putting this phi back into the variational principle, and you just have a variational principle now for one variable, which is again eta. Yeah? And you can write down this j explicitly as well. It has this form k minus some, this is the perturbed wave speed, which we talked about, multiplied by L. Look, and here's the formula for k, and here's the formula for L. You can actually do that explicitly. I thought that was really surprising.
Is that term a Lagrange multiplier?
Yes, you can think of it as a Lagrange multiplier if you want. Yeah.
In that case, you would think of L as being fixed.
You could do.
Okay.
I'll comment on that in just one transparency. Yeah. Okay. Buffoni actually did this for 2D waves. You know, there's for 2D steady waves, there's a remarkable formulation from the Benko where you can use conformal mapping to basically reduce the whole thing to a very simple pseudo-differential equation with a very simple non-local operator. and Buffoni did this kind of analysis for that equation. When I tried to do it with bare hands in 3D using this formulation, it worked, which I was really surprised at. It worked immediately and worked very well. And now let's just do the same thing as before. For beta bigger than 1/3, the action we think is around wave number 0. Otherwise, the action is around wave number plus or minus mu0. So let's take eta and let's split it into two parts, one near where the action should be, but this time, in 3D, and one part away. Then we'll get two equations. The Euler-Lagrange equation for this j, which is your j primed is equal to 0. You now get them as 2, and you can solve for eta 2 as a function of eta 1. Plug it back in and you get a reduced variational functional, and that eta 1, scale it either as kp or as Davy-Stewartson and plug that in and expand and see what comes out. And what do you know? You arrive at this reduced variational functional. Here I've written it as some leading order part plus order epsilon, some leading order part plus order epsilon. I'm lying here. It's not actually order epsilon, it's epsilon to some power. Yeah? But I didn't have the notes with me and I couldn't remember what the power was, but it doesn't matter. I mean, it's just a higher order thing. And it's just so beautiful, this. That is the functional for which corresponds to Kp, and that is the functional which corresponds to Davy-Stewartson. So you've really confirmed what actually the modeling was telling you. You now have a variational principle which is a perturbation of the variational principle for Kp or for Davy-Stewartson. Now you might say it's pointless having a variational principle for Kp because there's an explicit lump solution anyway. So really this is a special case of the variational functional for generalized Kp, but of course it's going to work for the Kp coefficient as well. And there you see the reason why at the very beginning I introduced these non-local versions of the equations, because that's the way they come up in these variational functionals. Okay, and now I'll just very quickly explain what to do, but I mean the idea is now clear. Yeah, you can look in the literature and find the variational approach for lump solutions of generalized Kp, it's Kp in this case, or of Davy-Stewartson. Dubois and so will be the reference for Kp, and Cipollati for the Davy-Stewartson equation. And basically you're just going to perturb just take their arguments and show that the arguments still work if you have a small perturbation. Of course, I've just written order of epsilon. I have more precise estimates on these remainders. I can control them in the right way so that the theories these theories continue to hold. Just to show you that I'm not, I've written down the function spaces in which you have to study these functionals, just to prove to you that there's nothing fishy going on. I mean, you can really say what they are. One thing you might be a little bit worried about, I decided to actually be honest about it. When we did the reduction on the previous transparency, look, we had these two parts, eta 1 and eta 2. Eta 1 had its spectrum concentrated around these points, so its spectrum has compact support. Yeah? So this eta, when you change like this, you will expect to see functions here, yeah, whose spectrum has compact support. But the way I've written it down here, that seems to have disappeared. It's actually the case that you can study those functionals in the ordinary spaces, and solutions of the Euler-Lagrange equations then will have spectrum of compact support. They must do, because you showed that there was an equivalence between what you started with and what you ended with. Okay, and then it's just, as I say, it's taking the arguments of Dubois and Saw or Cipollati and checking that they remain true if you add these perturbation terms. The keywords here are concentration compactness, and a little bit of fuss because you have non-local terms. That makes concentration compactness difficult, but the non-local terms are kind of quasi-local. So what I'm trying to say here is, suppose you had local terms like derivatives and you have two lumps which are moving away from each other. Say that these lumps have compact support and they move away from each other. Then obviously when they're far enough from each other, you can apply a derivative to one and to the other, and it's just a sum. But if you have a non-local operator, that's not the case. But quasi-local means you do have an interaction, but as the distance between these lumps goes to infinity, so the size of the interaction goes to infinity as well. And that's here as well. Tom inadvertently asked a question, which I will now inadvertently answer. I said concentration compactness, how to actually get minimizing or Palais-Mail sequences. You can do it in one of two ways. You can use mountain pass arguments on the J's, or you can reformulate the problem a little bit as constrained minimization, depending on what you prefer to do. Okay. Yes, and so there you are. That's an overview of what I know about this particular type of solitary waves. I mean, it's I know that those of you doing modeling aren't surprised when I say, oh yes, Kp and ds were the right equations all along. But now that's confirmed mathematically and to a standard which pure mathematicians are also happy with. I've gone over my time a little bit. Thank you very much for listening.
Questions or comments?
I think you were
First, it looked like
Me?
looked like you were
You.
first. I don't have a camera to check it.
Yeah. Your solution, solitary solution, it has two peaks and one bottom. And my question is there?
It doesn't really have two peaks. It basically has an infinite number of oscillations in the direction it's traveling, and then it's monotone in the other direction.
My question is,
KP lump.
Oh, excuse me. Sorry. Yes, the Kp lump.
yeah,
Let me find it. There it is. Yes.
that is there a solution which has only one minimum and no other maximum or minimum, relative maximum or relative minimum, only one.
Not as far as I know. There's no uniqueness theory for these type of waves, but if there is one, I don't know of it. This is actually just a plot of the exact solution to Kp, and the theory tells you that the equation you found for water waves is a perturbation of that, so it really does look like that. And the numerical computations look like this as well. Those are the only waves I know of this form.
That, such a kind of a monotone one peak solution is prohibited by the equation?
I don't know. I could guess an answer to the question, but the people here do more modeling than I do, so I'm too afraid to answer it.
You could make more complicated solution.
Oh, that sure. More complicated, yes. Absolutely. Yeah. Yeah, that I can do. Yeah, that I believe in. No, yeah. I think your question is it simpler? That's the question, Kevin. Yeah. Okay.
Okay, go for it, Harvey. You're next.
If I walked in to start here with your talk, I would get the impression that Kp refers to strong surface tension and Davy-Stewartson refers
Yes.
to weak.
That's right. That's what I said, isn't it?
Kp refers to strong or weak surface tension. Davy-Stewartson refers to strong or weak surface tension.
Okay. Then I have to clarify a bit more what I mean. So the equation I'm talking about here is, I think maybe the easiest way is to look at this plot. Yeah, I mean, when I have strong surface tension beta than 1/3, yeah, this is in 2D. If I have a dispersion relation which looks like that, then, and I do the modeling, the equation I get out will be Kp1, which is the correct model equation for strong surface tension. Yeah. Now, if I look at that plot, I could, here the critical values are either here or here. And if I do the analysis around here at a formal level, what I get at then is Kp2 for weak surface tension, and that will be corresponding to alpha is 1 plus epsilon squared, in fact. And if I do the analysis here, what I'll get out will be this version of the Davy-Stewartson, which is elliptic Davy-Stewartson. And that's all I'm saying is that for this minimum and for that minimum, the correct model equations are Kp1 and elliptic Davy-Stewartson. There are other versions of those equations which, at a modeling level, are the correct equations in different parameter regimes. That's all I'm saying.
I think what you're trying to say is Kp2 doesn't have interesting 3D localized solutions.
Sort of. I mean, it comes back to the debate on whether there are solitary waves without oscillations at infinity in 1D, right? Because if you linearize around that point, the problem there is that you're always going to have periodic linear waves resonating with it, and they manifest themselves then when you try to do the mathematics as solitary waves with oscillations at infinity. And then about 10 years ago, there were big fights at conferences of whether these oscillations could be zero or not. At a modeling level, of course, it doesn't matter, but for mathematicians, it does. I'm not saying they're not interesting. I'm saying there's a whole other story. Yeah. I mean, you could talk about, are there fully localized waves which decay to something more exotic at infinity? That's the question which you asked last week.
Okay. Well, isn't there the result of Walter Craig that says there are none in the gravity case?
Walter's result is that there are no gravity fully localized waves whose free surface is single-signed. Plus some regularity on it that has to be differentiable enough to satisfy the equations. But that's so basically he's saying without surface tension there are no very simple fully localized waves.
I have a question about stability.
let's just look at the Davies-Stewartson system, which is elliptic here. If you look at the stability of the solitons, I mean, if it's just a plane, you call it a line soliton.
Yeah.
You know, it's explosively unstable. What happens with your two-dimensional form?
I don't know.
You haven't looked at it.
I don't know, but I can tell you some things about stability. I can tell you that is stable in a mathematical sense. You have to take stability. I mean, I actually have 3 different existence proofs for that. One of them gives you information about stability as well. You can characterize that as a minimizer under constraint, in fact. And so you have some kind of stability associated with that. We always talk about this as conditional stability. The problem is that there's no global well-posedness results for waves close to that one, so you have to assume that the initial value problem has enough solutions nearby to talk about it. But if it does, then the stability result holds for that one. And for these waves, let me get them right. I can't find them now. For the line waves, yeah.
It must be unstable, huh?
Yes and no. There are families which are unstable, but I believe there are families which are stable as well. Stable means stable to 1D perturbations. Yes, they're all unstable. All the waves, all these waves are unstable with respect to those transverse perturbations.
Oh, really?
Yes. Actually, that's a side effect of the existence of the dimension breaking phenomenon proves that the line waves are linearly transversely unstable. The nonlinear instability of that wave has been studied by Jose and I forget the name of his collaborator now. I know that Eric is working on the nonlinear transverse instability of that with Jose as well. But the linear instability of those 2 waves with respect to transverse perturbations follows directly from the existence proof. It's basically the same spectral problem that you have to construct. Paul?
A bit to continue on the answer. I mean, these are not proofs, but numerically, the lump, the Davies-Stewartson lump, in the Davies-Stewartson regime is unstable to the focusing instability of Davies-Stewartson. But if you continue that branch to large amplitude, they become stable within Euler.
For water wave is stable.
And then again unstable.
And then there are stable lumps
There are stable machines.
in Euler.
Yeah. Are these results valid for beta close to a third?
There you have the interesting situation that when beta is equal to 1/3, you see these 2 points actually come together.
Yeah.
So you have a kind of degenerate situation. The correct model equation there is the Kawahara equation, which is a bit more complicated than these ones, and we haven't done the analysis for that. There are some other complications due to uniqueness of solutions and so on, technical issues. We haven't really looked at it in enough detail to give a definitive answer. I can tell you that there are line solitary waves near that point. They look sort of like a combination of, where's the thing with the, the line solitary waves look a bit like the transition between these 2. They more or less have this shape, but they do have oscillations superimposed on them which decay to 0, but they don't look like an envelope. So you really are in the sort of transition between the 2. That's the Kawahara dynamics.
Another question. At the moment what we are missing is the elliptic case for the modulation equation, isn't it? Why isn't that in your framework?
The elliptic case.
So the hyperbolic case. You know, you have the elliptic
Okay.
version, or
Yeah.
you have the hyperbolic version, and why you don't have the hyperbolic version?
Well, if you go,
Most interesting case for gravity waves.
okay.
Why? No, because it must be very subtle with your the parameters space you are playing. Because you're playing only with one parameter.
I'm simply saying if I go fishing in certain parameter regimes, then I'm getting the model it's basically motivated by the model equations. I know what the modeling tells me the right model equation should be. My interest is simply, do those correctly predict the solutions for the 4 Euler equations? And thus far, I've gone fishing in these particular parameter regimes.
The group velocity and the phase velocity have to be the same.
Yes.
In the regime
Yeah.
we are interested in, there are no lumps. And
Yeah.
therefore no point for this lecture.
Yeah.
Yeah, but it's an interesting regime for us.
Yeah, well, but there is no
We
lumps.
live in that domain.
Okay, remember, yeah, I mean, that's, your answer is exactly the right thing. I mean, I'm looking for solitary waves, so I need to go fishing where I think there should be some.
Yeah, yeah.
Yeah.
Yeah, but in that case, you also have at least line solitons.
Lumps, but they are stable.
They're not stable.
Not Davis Sturgeon.
Only 3D.
Not really stable.
You get soliton collapse.
No, you don't have collapse in hyperbolic.
Yeah, sorry.
Perhaps we can wrap it up on that point, and I have 2 orders of business left. The first is to invite everyone to the wine reception, which will happen right outside the store, and the second is to thank Mark for both organizing and speaking.
Thanks.